name is Mark Lanza, and I'm the president of the Motion Picture Sound Editors. Welcome to our Sound Device event for December 16th, 2020. We have opened this event up to the public because of COVID. We have a lot more sound device events coming up, so please check your email and the MPSE Facebook page for details. Please also check out the latest edition of our quarterly newsletter. It's currently posted at mpse.org, along with our new merchandise line that also includes this snazzy sweatshirt. So if you want to be cool like me, you need to order some MPSE swag. Anyway, I would like to introduce MPSE board member Eric Marks, who is the chairperson of our Sound Advice Events panel. Eric.
Thank you, Mark. Tonight's very special guest has published 2 books and over 20 papers on audio technology. He also is a former university professor and has a PhD in computer. He is the creator of Sound Particles, a sound design application capable of generating sounds in a 3D audio world. And he's the author of the new book, All You Need to Know About 3D Sound. I'm honored to be joined by Nuno Fonseca. How are you tonight, Nuno?
Hi, it's a pleasure to be here.
Yeah, thanks so much for joining us. So why don't you, tell us everything we need to know.
So it's a pleasure to be here. For me, I always loved the 3D sound and be able to do crazy things with 3D sound. And more recently at Sound Particles, we decided to create this ebook called All You Need to Know About 3D Audio. Essentially, this is based on several sessions that we have done at AES conventions in the past. And it's important to be able to bring this 3D concept to people with a very easy way, a very pedagogical way, instead of filling things with equations and math and those crazy things. So I really hope that you enjoyed. So essentially, I'm going to talk now today about these 4 main formats that are the most relevant nowadays: channel-based audio, object-based audio, Ambisonics, and Binaural. And so buckle up and let's start this heavy jam-packed session about all of these. So starting with channel-based audio, of course, we must start with stereo. So the idea of stereo is let's have 2 speakers. If we send the same signal to both speakers, essentially we're going to have a kind of phantom image, a phantom sound, the perception of a sound coming somewhere between the 2 speakers. And then if you change the gain of the signal in each one of those speakers, the perception of this sound source to be moving from one speaker to the another. And also quite important also is that this stereo setup, usually we talk about an angle of around 60 degrees, so almost like creating a triangle with equal sides. And this 60-degree angle is important because, of course, we could have a narrow angle and bring the speakers more close to each other, but essentially we would create a not so wide kind of sound image. We're going to have a much more narrow kind of sound image over there. But if you start increasing too much this angle past the 60 degrees, what happens is that your sound image is going to collapse, and instead of having this phantom image coming in the middle of the speakers, what is going to happen is that now the human is able to detect 2 sounds, one on the left, one on the side, and a hole in the middle. So essentially you get 60 degrees because it's more or less the maximum that you pretty much go with a good phantom image. More than this, and this starts to collapse. Then at some point people decided, okay, let's add speaker over here, so let's add 1 additional speaker between left and right. But a lot of people asking, but why? If we have the left and right and you are able with stereo to create a good sound image between these 2 speakers, why do I need this additional speaker over there? And essentially the reason why is that the world is not a perfect place. And in spatial audio, this means that not everyone can be on the sweet spot. Imagine that you go to a movie theater and it's a almost sold out session. You end up sitting on the first row, very close to the screen. And what is going to happen is that the left and right is not going to be at 60 degrees, it's going to be much wider than that. And what is going to happen is, once again, the sound image is going to collapse, and you are going to detect sounds coming from the left side and the right sound, but not in the front. So the reason for this center speaker is to almost act as an anchor in terms of sound imaging that helps creating all of this. And even if you are slightly off the sweet spot, the center image will help you make sure that you get a better experience even off center. Also, at some time, the movie theater, movie industry decided to explore other zones besides this frontal image. Initially with something called left, center, right surround. So essentially you had one surround channel, one audio channel that was fed into speakers. And later on with 5.1, this essentially you get separate audio contents, and you get a left surround signal and a right surround signal. Also quite interesting, when you go to the movies, although you usually have one speaker for left, one speaker for center, and one speaker for right, actually the surrounds are not reproduced with one single speaker, but with an array of speakers. And once again, the reason for that is the usual: world is not a perfect place, not everyone can be on the sweet spot. And what happens is that, imagine that you go to a movie theater, and instead of an array of speakers like you have nowadays, so nowadays you're going to have an array of speakers pretty much with 2/3 of the side walls and pretty much the entire rear wall filled with speakers. What is going to happen is that, imagine, for instance, that you go to a movie theater, and instead of that, they would simply place a surround speaker in each rear corner, and that's it. What is going to happen is that, for instance, imagine someone that is pretty much seated on the left side, very near the wall. So essentially what would happen is that you would have the left center, the left speaker pretty much almost in front of you. You're going to have the left surround pretty much behind you, several speakers on the right side, but anything will reproduce sound on your side. So essentially you're going to have this huge hole on the side of you, because everything else is in front, in the back, on the right side. So the idea of having this array of speakers is to make sure that, okay, you end up having a more diffuse sound, because there's not one speaker there, it's several speakers reproducing the exact same thing. But essentially the main goal is, okay, let's prevent the holes. And with this array of speakers, it allows you, it doesn't matter where you are seated, you are still surrounded with surround speakers on the sides and behind you. So that's the main reason for this array of speakers. Also, at some point, cinemas wanted to increase the impact of low frequency, especially for these things like earthquakes and explosions and all of those things. And of course, the problem with low frequencies is that the human ear isn't very sensible to low frequencies, which means that you need very high level of SPL sound pressure levels to be able only to start listening to them, and which means that you need much more power over there. And to handle this, of course, there are two possible situations. The first one, that apparently it's the obvious one, is, okay, let's simply have bigger speakers, more powerful amplifiers, and now we have enough power to put some low frequencies there. And apparently this seems the best solution. The problem with this is that, yes, it's expensive, but most important, it's important for us to remember that at that time we were talking about analog systems. The dynamic range was quite limited, which means that if you increase the power of the amplifiers to be able to drive these low frequencies there, essentially you are increasing the level of everything, and then you are also increasing the level of the background noise, and then that background noise, it's going to start affecting dialogue and things like that. So essentially this turned out not to be as a good solution as we could imagine, mainly because of issues regarding dynamic range. So the best decision at the time was, okay, let's create one additional channel. Let's call LFE to this channel. We already know that during reproduction, we are going to reproduce this, for instance, 10 dBs higher than the other channels, because this is low frequencies that need a lot of power and a lot of SPL levels to be heard. And then let's place a subwoofer. Yes, it's only one subwoofer, but low frequencies are not as directional in terms of perception. So the single subwoofer, it will not be an issue. And this is the main reason why we have LFEs and the subwoofers, instead of simply have bigger speakers and more powerful amplifiers. Also, through time, we have evolved to different layouts. At some point, Dolby has released 6.1 format. Also, we had Sony HRTFs with 7.1 with 5 speakers on the screen and 2 channels for surround. And then we have the traditional 7.1 that we have used nowadays with 3 speakers in the front and 4 speakers on the sides. And now we enter also the immersive audio. And when you talk about immersive audio, essentially, this is a term where we want to mention not only the surrounds, but also some height information. So the idea of immersive audio is to be able to reproduce sound that allows the listener to perceive sound coming from all directions, including from above or eventually even below the listener. And of course, with immersive audio, new formats started to approach from Auro, IMAX, 22.2 and many others. For instance, with Auro 11.11, as you see in this image, essentially you have this 5.1 traditional 5.1 system. Then with a second layer with height information, we have these 4 channels with an elevation around 30 degrees, and then above that you're going to have a speaker on the ceiling that is usually called the voice of God for obvious reasons, and essentially this allows you to reproduce sound, not only exploring the traditional 5.1 horizontal plane, but also with different heights everywhere. Also, we have different formats. For instance, the NHK 22.2 that was created in Japan. Essentially, you have this traditional horizontal plane, in this case with 10 channels. Then you're going to have some higher layer above you with many other, with 9 channels above you, 2 LFEs, and also these 3 channels that are located below the screen that will allow you to explore almost sounds coming from the floor instead of starting at the horizontal plane. So these are several formats that you get over there. And when I talk about channel-based audio, the main advantage of this approach is that this is the perfect approach if you already know what is going to be the output layout that is going to be used to reproduce your system. So if I'm doing something, a mix that is going to being reproduced on a single layout, and 100% sure that I'm not going to use any other kind of layout, or I'm not going to add additional speakers in the future to take advantage of more space resolution or whatever, this is perfect. The problem is that if I want to support different layouts, then I'm going to need different kind of mixes. So if I want to support both IMAX and, for instance, 5.1, I need 2 different mix. If I want Auro, IMAX, and 7.1.2 mix, then it's 1 mix for each one of those formats. So as you can see, it starts to not to scale very well, especially with different kind of layouts. So the question is, okay, would it be possible for us to create some kind of format that doesn't depend as much and on the output channel layout? Can we create something that it doesn't matter if it's outputted or reproduced with 10 speakers or 30 speakers? And that's the main reason for object-based audio, and also the main reason for the creation of Ambisonics. So let's now move to the next big flavor of the object-based audio. And when you talk about channel-based audio, the traditional one, once again, what we know is that, okay, we know how we are going to reproduce the system. We say, okay, I'm going to have these speakers on these predefined locations. So what I'm doing at the studio is simply to create the signals that I'm going to distribute and then going to be reproduced. So I'm going to have my sounds, I'm going to have a panner, depending where I want the sound to be positioned, this panner will create the right amount of signal to be sent to each one of those channels and distribute these output channels, and then I'm going to reproduce them. And this is pretty much what happens with channel-based audio. When we move for object-based audio, now things change. And what we do differently is that instead of mixing everything at the studio, what I'm going to do is I'm going to postpone the mix to be done only during reproduction. So I'm take the sounds, I'm not mixing the sounds at the studio, I'm sending the sounds independently, I'm going to distribute each one of those sounds completely independent, and then I'm going to use a special kind of panner that instead of applying the panning exactly at the studio, what I'm going to do is I'm going to send my intentions in terms of panning. I'm going to say, I want this sound to be positioned in this location. So I'm going to distribute all of this independent audio format and this information about where I want these sounds to be located. And then during reproduction, and based on the speaker layout that I actually have over there, that's where I actually do the final rendering of everything, the panning, all of those things. So if I'm reproducing something on the theater that has 10 speakers, yeah, I'm going to take advantage of that 10 speakers on the positions of those 10 speakers and take advantage of that. If I'm doing this on a movie theater, on that movie theater, instead of 10 speakers, I have 30 speakers. Once again, I'm going to see where the speakers are located, where the sound, the creatives want the sound to be located, and I'm going to do everything during reproduction. So the idea is I'm going to distribute my intentions, my sounds, and then depending on the reproduction system, I'm going to reproduce the system according to the speaker layout that I have in those systems. So once again, instead of mixing sounds to output channels, like we do with channel-based audio, what we're going to do now is, okay, let's keep each channel independently, not mixed. Let's add some additional data about their position, and we call this metadata. That essentially means data about data. And in here, we are talking about things like what is the 3D position of that sound source. We're going to talk about what is the size of that sound source. It's something almost like a pinpoint kind of sound source. It's something that is quite wide and many speakers should reproduce that sound. What is the movement that I want? All of those things. And then I'm going to simply distribute those channels and I call it objects. And then during reproduction, and based on the layout of the output speakers, based on the metadata that I receive for each one of those channels, that's where the render engine will decide what to play to each speaker. And all this is done in real time at the reproduction during this final render. Okay, so once again, sending all of this distribution and then doing all of this, the render based on the speaker layout. So, of course, when we talk about object-based audio, of course, Dolby Atmos is the most well-known format. With Dolby Atmos, we have support up to 118 audio objects plus a 7.1.2 bed. We're going to talk a little more about beds. So this means that Dolby Atmos supports 128 independent mono streams that I can distribute and send independently to the playback system. Also, the playback system is then able to support up to 64 independent speakers, which means that I can have up to 64 speakers completely independent, each one of those speakers with completely different audio being played back. Of course, if I look for a venue with Dolby Atmos, of course, the first more the thing that comes easily to everyone's attention is that now you have two rows of speakers in the ceiling, a left row in the ceiling and a right row in the ceiling. And the second thing that you notice is that although 5.1 and 7.1 speakers usually start around 1/3 of the side walls, so essentially covering 2/3 of the side walls, with Dolby Atmos now you add additional speakers to covering this gap between the screen and the first surround speakers to make sure that you are able to cover the entire 360 horizontal plane around you. And for instance, once again, to make a better perception of the kind of things that you're talking about, imagine that you want some sound to be moving from back to the front. In the 5.1, essentially what you do is you have these two channels, you have the left surround and the left channel, and essentially you send the audio to the left surround, and then you crossfade between these two signals, which means that you are crossfading between this block of speaker arrays and this left speaker. And that's it, crossfading between these two signals. When you're talking about Dolby Atmos and you want the same kind of movement, what is going to happen now is that you're going to use this speaker, and then this speaker moves, the sound moves to that speaker, and you are crossfading between these speakers. So you're going to have much more space resolution during this. And of course, you can have this if you want a kind of a pinpoint kind of sound source. If you have a more wide, eventually it could be these two speakers playing at the same time and then moving to these two speakers and then to those two speakers and so on. So as you can see, you get much more resolution instead of simply doing something like this and crossfading between these two signals. And of course, the experience from the listener is going to be much better. Besides objects, most of these object-based formats also support some sort of channel-based audio. So the idea is, yes, we have objects, but sometimes we want to use channel-based audio. And in case of Dolby Atmos, you have a 7.1.2 pad, which means that if you already have some material that was created as a channel based like 7.1, for instance, the music was mixed in 7.1, or imagine that you have a soundscape that was the sound designer have created in 5.1. So you are able to create all of this and simply use a bed, because since the beds have locked positions, you can mix all of those sounds to the same bed, all of these stems to the same bed. And then you simply use objects for specific sounds like a car passing by or something like that. Of course, we've talked about Dolby Atmos, but there is other formats of there like Auromax or DTX-X that also use the same concepts. So about object-based audio, what are the advantages? The big advantage is that it works with any layout. Okay, it doesn't matter if it's 10 speakers, 20 speakers, 40 speakers, whatever you want. It works with every one of those layouts and gives you the best space resolution for any one of those layouts. So if you have 20 speakers, great. If you have 50 speakers, even better, because you take advantage of these additional speakers that you have over there. What are the disadvantages? Well, disadvantages is that you need to distribute a lot of channels. And for movie theaters, this eventually may not be an issue, but if you are doing streaming or if you are sending, distributing things in an optical format like a Blu-ray or something like that, this could become an issue with a lot of data that you need to distribute. And in some cases, what you end up doing is you end up reducing the number of objects, and you say, okay, instead of sending 128 objects, let's simply send the bed and some additional like 8 objects or something like that. So eventually you end up doing some kind of restraint on the format. And also eventually this could be a limited number of input sources. So 128 sound sources, it's pretty much a good number for most projects. But for instance, in Hollywood productions, you may have as 1,000 tracks of audio, which means that you cannot use every single track as a different object. You need to use some of them mixed as BET because you are limited to 128, or for instance, as using sound particles, we have renders. I have renders up to 1 million sound sources that, of course, I cannot use only as objects because it's limited to 128 Dolby Atmos. So there is several things that eventually, once again, eventually could be a limit. Just of curiosity, people know this movie, Fantasia from Walt Disney. It was released in 1940. At the time, since the movie breeds and lives based on music, because all the movie is based on music, Walt Disney decided that it was interesting to have a special sound system for people to take the most experience out of it. So it was created something called the Fantasound. There were several models, even with different kind of features. This was installed in several theaters. In some cases, it even went on tour through the United States, traveling from city to city for people to see the movie with the best sound experience. This is considered the first movie to use surround sound. Also, some Fantasound systems have a ceiling, a speaker on the ceiling. So this also makes this movie the first immersive audio movie to be released. And this was created essentially with a 4-track system. So it was, people have recorded 3 tracks of audio, and then there was one track was used to control the routing of these 3 channels regarding the speakers. So essentially this 4th track would control all each one of those audio tracks. 3 audio tracks will then be routed to the speaker. So from my point of view, this is the first object-based audio movie. Yes, it was not digital, it was analog, it was a discrete, not like current object-based audio, but nonetheless, I continue to be impressed with a movie that is now 80 years old, and how innovative it was for the times and how intelligent and bright people working on this project were at that moment. So a full curiosity. Okay, so now let's enter the new domain, because what I've talked so far, pretty much most of you already know channel-based formats and Dolby Atmos. So let's talk now about something a little more complicated, and that's Ambisonics. But before even talking about Ambisonics, let's talk about a simpler cousin, that is the middle side. So the middle side is a technique widely used for recording stereo. Essentially, what we do is we use 2 microphones, a cardioid that is pointing to the main source, and then a figure of 8 pointing to the sides. And the idea here is the cardioid will essentially capture the main sound from the source that I want to capture, and then the figure of 8, since the figure of 8 is pointing to the sides, essentially it's not going to capture anything coming from the front, and essentially this captures almost like the non-mono component of the sound. So in the end, of course, we then mix the 2 together, mid and side signals, to create the left channel, and we invert the phase of the side mixed with the mid to create the right channel. And once, like I mentioned, this is a widely used recording technique. Many sound engineers like this technique to recording stereo content. But the interesting thing about middle side is that middle side can also be used as a matrix techniques, which means that I can convert stereo to mid side and then convert mid side back to stereo, to left and right. So for instance, imagine that you want to increase the stereo effect of a stereo recording. For instance, you can take left and right, convert to mid side. You can then take the side signal, increase its amplitude, its gain, and then convert back to left and right. And by doing this, you are increasing the component that is not mono, so you are increasing the stereo effect. Or eventually something that is also used a lot in mastering. Imagine that you are doing the mastering of some song and you want to make a small equalization on the main voice. Of course, at that time you no longer have access to the individual tracks, so you only have access to the final stereo. You have two choices. The first choice is to simply apply the equalization to the entire stereo. The second choice is convert left and right into mid and side. Then you can equalize only the mid signal, which means that you are equalizing only the signals of the sounds that are on the center, and then convert back to the left right. So essentially in here what we do is, if we mix left and right, you end up with this mid that represents the mono component of the signal. And then if you have left and you remove the right, essentially you are removing everything that is common to the both signals. So this side, it's representing the non-mono component of the signal. And then for those that like math, you can convert back this into left and right by simply mixing mid and side once again. And it's important to mention this because there's now some things that we're going to talk about Ambisonics that it's important to get this historical grasp at the middle side, and you're going to see in a few moments why I bring this up. So Ambisonics was created on the 70s, and the idea was, okay, let's create a format that is independent of the reproduction system. So let's create something, I record something in Ambisonics, and then I will able to reproduce this in mono, in stereo, in 5.1, with a system with 6 speakers around me, or 80 speakers, or quad, or speakers above you and below me. So that's the main reason for Ambisonics. So essentially what happens with Ambisonics is, okay, we're going to have the first channel. It's something that is equivalent of recording something with the Omni microphone. So essentially the first channel, it's the mono component. It's everything that is happening around this audio seed. So imagine placing Omni microphone and capturing everything. Okay, so that's the first channel. And this represents, it's the equivalent to the mid of the middle side, the mono component. And then instead of using one figure of 8, as we used in mid side, now let's use 3 figure of 8, one for each direction. So you're going to have one figure of 8 pointing to left, right, another one front, back, and another up, down. And by having this 3 figure of 8, we are actually capturing information about all these 3 axes, all of these 3 dimensions. So essentially, when you talk about Ambisonics, you are using these 4 channels, 1 with mono and 3 with 3 figures of 8. And sometimes people think, okay, Ambisonics, this is black magic, and I don't know exactly what is over there. But once again, Ambisonics is regular audio like all the other things. Of course, we cannot feed these signals directly to speakers. Yes, actually you can feed to the speakers and going to reproduce audio, but it's not going to give me a sound image like in stereo or in others. So what I need to do is, like middle side, I need to decode them first. So the same way that middle side has audio, the mid and side are perfectly audio that I can process and do whatever I want with them. They actually need to be decoded back to stereo to be used, and the same thing happens here. So I have these 4 channels. They are audio being recorded, but if I want to get a sound image, I need to convert them and decode them to be able to use that. So, okay, imagine that to say, okay, I like the concept, so let's do some Ambisonics recording. Of course, like I mentioned, you can do these recordings using an Omni and 3 figure of 8, okay? But if you start doing or try to do some recordings like this, you're going to see that it's not very practical to try to position one Omni microphone and 3 figure of 8 with pointing in different directions, all of those capsules as close as possible, because if they are not very close, you're going to start having issues with phasing and things like that. And so at some point, people figure out that there is a better way of doing Ambisonics recordings, and essentially is by having these tetrahedral microphones, as you see here on this image. So essentially it's 4 cardioids pointing on these directions. This will give you these 4 signals. So each one of those letters, this represents the capsule with the left front up, right front down, left back down, right back up. So the directions of each one of those capsules. And then by using some kind of math, what you do is you convert these signals from those 4 capsules into these omni and figure of 8 kind of patterns. And it's important that the signal that comes directly from these microphones is what we call A format. Okay, so it's one of those signals, it's a cardioid being used. And then you have this format with omni and 3 figure of 8s that we call it B format. So Ambisonics, most of the times you are working about B format. Sometimes when you're doing recordings, you have this in A format, and it's important to convert this as soon as possible into a B format. Usually the microphones bring a plugin that will automatically do this conversion between A format to B format, and then we continue processing everything as B format and using Ambisonics as a B format. Okay, so now we have this concept and these microphones and all of these things. So does this mean that we can get accurate 3D space representation using only 4 audio channels? Well, not really. So yes, you can use Ambisonics, and Ambisonics give you 3D information using only 4 audio channels, but is not very accurate. What is going to happen is that even if you have a sound source that is captured or rendered in Ambisonics, all of those sound sources are going to be very fuzzy, almost like autofocus. Just to give you a visual idea of things. So imagine that I have a sound source, I'm capturing this with Ambisonics, and now imagine that I'm going to decode this with 100 speakers or something like that. What is going to happen is that that single sound source is going to be reproduced as this entire higher area over here. So several speakers playing at the same time with everything. So as you can see, this is not give you very accurate space representation of the sound. And that's the reason for something called high ordered ambisonics. And the reason with high ordered ambisonics is, okay, let's add some additional audio channels. And by adding these additional audio channels, we are going to increase the resolution of the system. So as you can see in this image, you have these 4 above speakers patterns. So you have this omni, okay, a pattern over here, and then this 3 figure of 8s. And this is first order ambisonic, these 4 signals. If you want to increase the resolution, you can add more 5 channels, which means now you're going to use a total of 9 channels, and this is called second order ambisonics. If you want to increase even more the resolution of the system, you can add more 7 channels. You get now third order ambisonics with a total of 16 channels. So it's a matter of simply adding more channels to the system to increase the resolution. The same concepts still apply, but you are improving the resolution of the system. And of course, we don't have microphones with these crazy polar diagrams that you see over here. What you do is something pretty much the same way that you do with tetrahedral microphones. So you get, in this image, we get the Eigenmic, a well-known high-order ambisonics, and we have several capsules over here, and then with some kind of plugin, you convert this to regular ambisonics like third-order ambisonics. So when you talk about ambisonics, there is something that is very, very important to know, because ambisonics, it's been around almost like 50 years. So there are a lot of evolution that happened in the middle. So you need to be careful, because sometimes you are working with ambisonics and you're talking about different kind of flavors of ambisonics, and you can have some problems because of that. So the first thing that you need to know is, okay, which order I'm talking about. It's first order ambisonics, is second order, is third order, is sixth order, what order it is it. And the good news is that it's only a matter of looking at the number of channels that will give you this information. So if I have 4 channels, it's definitely first order. If I get 9 channels, it's second order. If I get 16 channels, it's third order, and so on. So by looking at the number of channels, you already know which order are we talking about. The second thing, quite important, is, okay, imagine that someone send you a recording and say, okay, this is the recording that I've done with my Ambisonics microphone. So the question is, okay, is this audio stream, these 4 channels, in B format or A format? Because if they are simply the recordings of each one of those capsules of the microphone, then it's A format. But if they are already been converted properly for Ambisonics, then we have them as B format. So it's quite important, because if I'm working with this and actually this is a format and I considered it as being a different kind of format, imagine someone sent me already in B format, and then I thought, no, it probably is A format, so let them convert this to B format. So it's going to get problems around. The third thing, quite important, is the ordering of the channels. So originally we used something called the FUMA, and later on, especially because of high order Ambisonics, we changed for ACN. That is something that scales better for high order Ambisonics. But once again, if you are working with old systems, eventually could have a different ordering of the channels. So if you start working with Ambisonics, and at some point you start to notice that the sounds that should come from the front are coming from the left or coming from above you or things like that, probably you're going to have an issue with channeling ordering. You considering that was an order, and after all it's another ordering of the channels. And third, and quite important also, is the normalization. And normalization regards the gains of each one of those channels of the Ambisonics. Nowadays, we use something called SN3D, and the advantage of SN3D is that with this normalization, it makes sure that the first channel, that Omni channel, is always the channel with the highest signal. So if you are looking at the view meters, if the first channel is not clipping, then you are rested that all the other channels will not clip also. The other previous normalizations had some problems. Sometimes you have a sound in one location where you don't get any kind of clipping, but they start moving, and simply by moving, you start having clipping on the other channels. So SN3D allows you to make sure that the first channel, the Omni, is always the one with the strongest signal of all. Also, when you're talking about people and you are sharing data and things in Ambisonics, sometimes people tell you, okay, I'm using Ambix format. So Ambix, actually, it was a file format that nowadays is not used anymore, but nonetheless, Ambix used B format, ACN, and SN3D. So nowadays, when someone tell you that they are using Ambix format, they actually mean that they are using B format, ACN, and SN3D normalization. So once again, the good news is that nowadays people use this SN3D and ACN. Yes, you have some problems with B format and A format. So make sure if you are exchanging Ambisonics recording between people, to make sure that people understand which format are you talking about. Is still the A format still recording directly from the capsules of it, or if it was already converted to the B format. But nonetheless, if you are especially working with old recordings or old Ambisonic systems, be careful, because channel ordering and normalization could be an issue. So this is only a list with the number of channels that you need depending on the order. If you want, for instance, 6 order Ambisonics, you're going to need 49 audio channels to use as Ambisonics. Also, the interesting thing about Ambisonics is that it's very easy to apply rotations to the Ambisonics. So imagine that you have your sound field, your recording, but you would like to make some slight rotations to it because, for instance, the microphone was not perfectly aligned with the 360 camera or something like that. So it's very easy to do rotations with Ambisonics. And actually, that's one of the reasons for the use of Ambisonics in VR applications. So if you notice, Ambisonics is perfect for VR because first, okay, gives you 3D audio, great. It has a low channel count, starting at 4 channels. So once again, it's great for web or for mobile and other kind of VR applications. And also it's very easy to do rotations. And if you notice, VR essentially it's all about rotation. So you are rotating your head to the side or up and down or tilting your head. So essentially VR, it's mainly rotation, rotation, rotation. So once again, Ambisonics is great to do all of these. And VR applications was the main reason why Ambisonics started to come out once again after being so many times, so many years almost forgotten, back to the stage and be an interesting approach for a spatial audio. Also, when you talk about Ambisonics microphones, of course, Ambisonics microphones give you much more space information than traditional mono or stereo, but there are 2 important lessons that we have learned from stereo that is important to also take into consideration. The first one is that Ambisonics microphone will not resolve all your problems. Sometimes I talk with people that think that, okay, now I have an Ambisonics microphone, I place the Ambisonics microphone somewhere, and now I'm going to capture my entire sound, all my production sound, and everything is fixed. So the same way that if someone asks you to record the sound for a movie that is going to be released in stereo, the same way that you don't say, okay, let's simply place a stereo microphone on top of the camera and everything, all my issues are handled. No, we're going to do, no, I'm going to need some lavalier microphones on the actors or a boom or something like that. And then in post-production, I'm going to position things on this, and I want those sounds to be positioned and so on. The same thing happens with Ambisonics. So imagine if you are doing a movie, a 360 movies, yes, Ambisonics microphone can give you fantastic results, but nonetheless, you still need to think about post-production and getting clean signals. So probably you're still going to use lavalier microphones on the actors and things like that. So be careful, because sometimes people think that Ambisonics microphones are the silver bullet that will handle all of those problems. Once again, gives you much more space information than mono and stereo microphones, but it's not the silver bullet that will fix all your problems. The second thing about Ambisonics microphones is that they will not give you one important dimension, and that's time. So Ambisonics microphone works as a coincident microphone, almost like XY kind of a microphone. So you get all the capsules very close together to make sure that you don't get phasing and those kinds of problems. But sometimes you want different kind of perspectives in terms of time. And the same reason why top sound engineers that record orchestras, they don't go there and simply place an XY microphone and on top of the conductor and receive a Grammy for the best orchestra recording. No, they decide to let's have several microphones in different positions of the stage or different positions of the audiences to get the best recording and to get these high decorrelated signals that then helps give much more width and much more 3D spaciness to the recording. So the same thing happens in here. So Ambisonics is great, give you a lot of interesting dimension, but sometimes you want even much more than this, and you want to explore time and be able to use microphones spaced between them to get this decorrelated area and this decorrelated kind of sound. So Ambisonics, let's see, okay, pros, works with any layout like object-based audio, which is great. So you do a recording in Ambisonics or you mix something in Ambisonics and then you can reproduce this whatever you want, okay? And second, it gives you 3D sound using a very small number of channels, starting with only 4 channels. And these are very interesting advances of Ambisonics. The disadvantages of the Ambisonics is that you really need additional channels to get good space resolution. Okay, so if you really want space resolution, you're definitely going to need much more space information. For instance, imagine that you do something as a 5.1. If you convert that to first order Ambisonics and then convert back to 5.1, you're going to see that a lot of space makes a lot of things start to overlap. So once again, if you want, eventually, if you want almost the same space resolution that you get with object-based audio, you'll probably need something like 6 order Ambisonic with 49 channels or something like that. So once again, Ambisonics is great, it's fantastic, gives you a lot of things, a lot of features with a small number of channels. But if you really want good space resolution, then you're going to pay the price of adding much more audio channels. It's not going to be 4 or 9 channels, you're going to need much more than that. And finally, let's now enter the final stage and this final group, that is binaural. And essentially, when I talk about binaural, I'm talking about the perception of 3D audio using headphones. So the question is, okay, can we really simulate 3D sound using headphones? And the answer is yes, the same way that we only have 2 ears and still we are able to capture everything from around us and get this sense of 3D sound using 2 ears. If we use headphones, we still be able to do that. So how can we implement this? How can we create binaural sound and have this sense of 3D sound over headphones? But before, let's once again remember how the brain and how everything, the human, detects the direction of things. So imagine that I have a sound like in this image coming from the right side. So one of the most important clues that you're going to have is something called interval level difference, which means that the sound will arrive to the right ear stronger and weaker to the left ear. The second thing that is going to do is called interval time difference, which means that the signal will arrive first to the right ear and then later on to the left ear. And in here we are talking about a difference that can go as high as almost 1 millisecond, but even being quite small difference below 1 millisecond, it's enough to give the brain information about the position of the sound. And although these 2 main cues are the 2 most important ones for us to detect the perception of the sound, they don't explain you, for instance, the difference between the sound coming from the front, above you, or behind you. Because in this, for instance, these 3 situations, you get the same level at both ears, the same time, they arrive at the same ears at the same time, but still we are able to detect from a sound coming from the front, top, or below you, behind you. So what is happening? Well, essentially, it's all about these strange accessories that we have in our heads called the ears. Okay, so this outside here, the pinna, have all of these curves and this very strange shape. And what is going to happen is that depending on the position of the sound is going to be reflected in different parts of the ear. By being reflected in different parts of the ear, essentially the sound arriving to the inner ear is going to be the direct sound and these reflections. As you know, when we mix the original sound with reflections, you're going to have come filtering. So it's going to act almost like an equalizer. So what is going to happen is that depending on the direction of sound, the ears are going to act as equalizers. It's going to change the frequency response of the sound depending on the location of that sound. Besides that, there is also some shadowing effect. So a sound over here needs to bend around the head. With low frequencies, it's easier for low frequencies to bend. Higher frequencies tend to have more difficult bending. So essentially what is going to happen is that at higher frequencies, you're going to be more attenuated in this here because of this shadow effect. And finally, there is another factor, although less relevant, that is the shoulder reflections that you're going here from our shoulders. But pretty much this is the main things that help us detect the direction of everything. So we know this, so how can we characterize this or capture this kind of behavior? So if you notice, essentially we are talking about things like amplitudes, timings, delays, filtering. So all of these can be captured using impulse responses. And the same way that we can do an impulse response of a room and capture the reverb and then use convolution to apply that impulse response and some signal, we can do exactly the same thing regarding the behavior of the ears. And for that, what we do is, for a particular position, what we do is capture the impulse response of that position regarding the left ear and regarding the right ear. And then those impulse responses, you usually have a name for it. You call them head-related transfer functions or head-related impulse responses. They are exactly the same thing. The only difference is that transfer functions are on the frequency domain, where impulse responses are on the time domain, but essentially they mean exactly the same thing. It's like having a recording and looking at the waveform or looking at the spectrogram of that recording. So they are exactly, in practical, the same thing. Some people use the term HRTFs, some use the term impulse responses, but essentially it's those impulse responses regarding one position and the impact of that position to the ears. So how people create these data sets? Well, there are several ways. One of them is to use these dummy heads, like you see here on the image. This one is from Newman. Essentially, you have this shape of the ears. You have a capsule position on the inner ear, equivalent to the inner ear. And by using this, you get a sense, the same behavior as a human head. Or eventually, you can use actual humans and simply place small microphones on the ears of those persons and capturing the impulse responses from that point of view. And then the idea is to, okay, let's try to capture several positions around the listener to then record and create these data sets. Of course, there are data sets already available. These are some of them. Pretty much most software developers already use these data sets available to implement their binaural plugins or to create their binaural engines for video game engines or something like that. So what happens here is, now imagine that I have a signal. For instance, I'm in Pro Tools. I have the sound of a helicopter. I'm trying to do a mix for a binaural audio content. So what I do, so essentially the plugin, if I'm using some binaural plugin, the plugin will look at the data set. We'll try to see what is the position from the data set closer to that of the user that the user have selected. Eventually, you can even interpolate between existing positions. And then I'm going to simply, the plugin is going to do a convolution and apply that, the left impulse responses to the signal, send to the left here, and do the exact same thing with the right impulse response and send it to the right here. And that's how we get the binaural. So binaural, it's the main approach nowadays with 3D sound over headphones. It's used in video games, it's used in VR. And great, so now we have 3D sound over headphones for everyone, right? Well, not really. What is the main problem? Well, the main problem with binaural is that each person has different head sizes, different ears. The shape of the ears are completely different. The size of the ears are different, which means that the impulse responses that we get is completely different from person to person, which means that I could be using an HRTF data set, okay? That data set could work very well for a lot of people, but will not work for other users. And for you to give a better sense of what I'm talking about, I'm going to show you this graphic. So essentially what I have placed here, this is the the frequency response of a sound coming from the front, from the equivalent of the center speaker, for 30 different persons. And as you can see, the frequency response of these impulse responses is completely different depending on the users. So as you can see, up to 1 kilohertz, things are pretty much flat without, there's some level, but only in terms of level, okay? From 1 kilohertz until 5 kilohertz, you start having some variation, okay? And then from 5 kilohertz above that, then it's a madness. And as you can see, each person has a completely different frequency response regarding those sounds. And once again, if you look at the scale, you're going to be astonished, because we are talking about difference that can be as high as 30 degrees between users. So I could have the two persons listening to the same sound, and the difference in levels in some frequencies, what arrives to the ear of that humans can be as high as 30 degrees of difference between one and the other. And even if you try to create almost like an average and say, okay, let's create a data set that pretty much it's the average of these crazy curves over here, what is going to happen is that even if you go like an average kind of thing, you end up still 15 degrees of difference between what it should be and what you are actually getting. And sometimes when I talk about binaural, it remember those crazy 3D glasses that from paper that we have seen movies like The Monster of the Black Lagoon and things like that, that yes, he gave us a sense of depth, but completely ruins the colors and ruins the photography. So the same thing happens a lot with binaural. So we use binaural sounds and pick up our plugins using binaural. And what happens is, yes, you get this sense of 3D space, but what is going to happen also is that are completely ruining the frequency response of the sound, because the kind of sound that I was hoping to receive on my ears using a speaker now are coming with variations up to 15 dBs or even higher. It's almost like, okay, I'm using binaural, but then I'm doing a fantastic mix passing through binaural, and it's almost like having a graphic equalizer where someone simply go there and select random positions on the sliders of the random equalizer. So once again, what is going to happen when I listen to a sound in binaural, okay, or when I listen to a sound period, my brain, what is going to do is try to identify based on the years and years that we have always listened to sound and say, okay, this kind of sounds, does this sound have a special kind of shape that I usually associate with a particular direction? Yes or not? Because if this has a more or less a kind of shape that I already identify, okay, this is coming from this direction or that direction or the other direction. If I receive something and I'm not able to detect the kind of shape, the kind of frequency response that I usually get from different position, what ends up is that the brain is going to give you wrong information, and probably you're going to listen to the sound inside your head instead of outside. So a lot of things start to happen. So what happens in real life is that most systems try to do what is almost like a baseline HRTF, that essentially, okay, let's try to create a data set that is not so bad for everyone. So it's not perfect, and it's not good for everyone, but at least is the least worst data set that I may have. For instance, if you go to YouTube and you download a 360 video and listen to it with binaural, of course, what they do is to, okay, let's create one data set that we believe it's more or less an average kind of data set that will work pretty much more or less with everyone. So that's pretty much what happens. If you really want to do binaural the right way, then you need to customize these HRTFs, and each person that is listening to this needs to have a customized HRTF to get a good experience with it. And this could be with different approaches. Eventually, it could be someone that simply allows the user to select the best from multiple. Okay, for instance, that's what we decided to do inside Sound Particle. So you can go there and pick up, like, we have probably 100 different data sets. Okay, it's a tedious operation, but you are able to select the best one for you, and still probably not going to be perfect. Of course, there is also something called the SOFA files. That essentially it's a file format where you can have your own data set. So if you work in a university, or if you have the ability to capture your own impulse responses, your HRTFs, great, you can have this on this file system. But once again, it's quite important to have this HRTF available to take good advantage of binaural. So when you talk about binaural, pros and cons, once again, pros, you get 3D sound with a simple and cheapest setup using headphones. I don't know anyone that doesn't have headphones. So it's very cheap. You don't need 20 speakers around your living room. You simply need headphones, and that's it. You get 3D sound, perfect, cheap, great. What is the problem? Well, the problem is that you're going to have a source of many problems if you don't use individualization. If you're not able to adapt binaural to that person in particular, you're going to have problems, and that problems could be things like front to back confusion. A sound is in the front and the listener thinks that's on the back, and vice versa. Things like externalization, it means that the sound, instead of being outside your head, it's you perceive the sound as happening inside your head, almost like when you listen to regular stereo with headphones, or other problems as simply the frequency response that is completely off and completely ruined. Yes, you notice the 3D positions, the sound is over here, over there, and so on, but the frequency response is completely off what you really wanted. So binaural, it's of course a problem. So in conclusion, okay, we have these 4 different approaches. All of them has advantages, all of them has disadvantages. I believe that sometimes when you talk about 3D audio, sometimes you tend to polarize too much this discussion. Almost sometimes you have almost like a religion kind of topic. You have the religion of the Ambisonics or the religion of object-based audio, and people tend to polarize things and follow, no, Ambisonics is the answer for all the problems, and then the other ones will say that object-based audio are the answer to everyone's problem, and so on. So once again, I believe that there isn't a single approach that is best for any situation. So there is situations where channel-based audio is still the best, situations when object-based audio is the best, situations where Ambisonics is the best, situations when binaural is the best. So all of them have advantages and disadvantages. That the main reason for this talk and the book and all of this is to, okay, help people to understand more about these formats, the problems and the advantages and disadvantages of all of them. Of course, in many cases, we end up having hybrid approaches. For instance, Dolby Atmos, we have object-based audio and beds, channel-based audio at the same time. Sometimes you have a mix of binaural with other formats, so channel and binaural, or object and binaural, or Ambisonics and binaural. So sometimes to get the most of the systems, you end up mixing and create this hybrid approach between them. And I hope that you have now a better understanding regarding 3D audio. Of course, if you want, you can go to our website and get the free book. What I've talked today is pretty much 80% of the things that we discuss in the ebook, but nonetheless, if you are curious, go to soundparticles.com and look for the ebook. And finally, of course, you can, on a shameless self-promotion topic now, of course, you are free to use to try the Sound Particle software. It's the wonderful playground to explore all of those things if you want to explore binaural and Ambisonics and all of those things. So definitely to those that don't know Sound Particles, you can create very interesting things with all of these. Each one of those points that you see on screen represents a different sound source, so you can generate like 10,000 sound sources around you and things like that. So once again, this is pretty much what I have in mind, and now I'm more than welcome to answer all your questions.
Thanks so much, Nuno. Yeah, that was incredibly informative and detailed. Yeah, if you have any questions, everybody, please post them in the chat. I see we already have one. Adela asks, if I'm understanding it correctly, all 4 approaches utilize mono audio channels moved around in space to create a 3D effect. How does this work in music with stereo channels or stereo effects like a reverb or a stereo delay? Okay,
so starting when you talk about channel-based audio, of course, we have these channels. So stereo is channel-based audio, 5.1 channel-based audio. When you talk about object-based audio, although each object it's mono, but you can create multiple pairs. You can create pairs or groups of several channels. So eventually you can use a stereo material, okay, and then use as 2 different objects and simply move the objects around and still continue to have a stereo, but it's a stereo that is moving around. And if you are using Ambisonics, they are you can still create sound sources in Ambisonics and render these stereo sources as Ambisonics. And in binaural, you can still consider the position of the left speaker and the right speaker to make sure that you are rendering in binaural with all of this. So the fact that we are talking about monophonic audio streams doesn't mean that we are losing things in music or something like that. No, we can still look at stereo as being 2 mono signals that actually they are not in mono, they are more than that. So in music, there are several things that can do. Of course, you can, people, for instance, Dolby are now betting a lot in the Atmos for music, and there is a lot of things that you can do with music. You can do things like reverb. You can even do things more interesting than stereo reverb. So because you can now create reverb that is in 3D, completely decorrelated, so it feels much more natural. Because sometimes the problem with reverb is that, okay, I'm listening to reverb in stereo, but what is happening is that I play the stereo with 2 speakers and all the sound comes from those 2 speakers, and all the reflections that I get, all the reverb that I get there also comes from those 2 speakers. And now if I use spatial audio, I'm able to get much more sound coming from all directions. So it feels much more natural, much more decorrelated. So it's even, for me, it's completely a new upgrade. The only challenge, the main challenge that you get probably regarding reverb is that imagine that you have now a signal, an object, okay, and you say, okay, I have this object that is moving around. If I want to add reverb into that, since you cannot simply place the reverb on top of the object using the same audio stream, because otherwise the reverb will also move around and it's a very localized kind of reverb. So you need to almost have probably a bed and using a bed as a reverb to make the reverb coming over there. Nonetheless, once again, in music, that are fantastic things that you can do with spatial. Sometimes people, once again, like in surround, when surround arrived, people thought, okay, yes, surround is great. The first people mixing and using surround started to play the guitar on the back, and the other drums starts to panning completely around you. And yeah, it was great for the first times, but people say, oh, no, I still want the band playing in the front. I don't want the band playing behind me or things like that. But even if I simply play everyone playing in the front, the fact that I have surround speakers, it's great because the reverb is going to feel much more natural. Even if I simply use the left surrounds to add reverb, is still going to get a much better kind of sound, even with the band and most of the musicians coming from the front. And the same thing also happens in here. So with now immersive audio and 3D audio, what you're going to do is it's even better to get all of this. Even in terms of mixing, when you have only, for instance, stereo or even 5.1, you are simply adding too much channels, too much content to the same speakers. So which means that you're going to have a lot of frequencies colliding. When you start moving to things like Dolby Atmos or Ambisonics or other 3D formats, what it's going to do is now you have much more speakers to spread your material, and they are not going to collide frequencies against frequencies and so on. So even for music, I still believe that 3D audio will be much better way to use and to serve your material than simply use regular stereo or regular surround.
That's great. Thank you. Any other questions from the audience? If not, I have a couple of my own, but I would love for you guys to ask any questions that are on your minds for Nuno. Nuno, would love to hear how your book came about.
So essentially, I've started doing presentations like this one in AES convention. I have proposed to do an initial presentation, and then the organization of the event started to ask me to repeat the same session on upcoming conventions. And at some point, we were also talking with people, and people sometimes asking us the same amount of questions. And that is something that we thought, okay, probably instead of simply answering this, let's try to create an ebook and simply pretty much take the work that I've been doing with these AES presentations and simply, okay, let's write a book. And that's exactly what we have done. And once again, taking the advantage of now having more people working with me and be able to get a designer that help us with the images and get someone to cover review the English and all of those things. So that's the main reason for us to, okay, let's release an ebook. And of course, it's free. Our goal is not to earn money from the ebook. We simply want more people about all of those things. So that's pretty much what we have done with the book, is to, okay, help everyone understand, because once again, people sometimes are more common to the things that they work daily. Probably, for instance, if I'm working with cinema, probably I'm used with channel-based audio and object-based audio, and I don't know much about Ambisonics or Binaural, or sometimes people mainly work on particular things like in music, mainly with stereo, and they have questions about Ambisonics or Binaural, and so it could help everyone with all of this. So that's the main reason. That's
great. We have an audience question from Israel. Can you talk about sound particles and how the workflow works? And I just want to add to that. I know this tech is currently being used, has been used in a lot of studio films. I'm just curious how it's been used on these films.
Okay, so essentially what we have done with sound particles is to completely create a new paradigm of software. So when it comes, let me compare it with image. So when you talk about image software, you usually have 2D and 3D image software. You have 2D software like Photoshop or a video editing. You work mainly with pixels. We simply layering things, images on top of things. And then you have different kind of approach like 3D native software like Maya or Blender, the kind of softwares that you use by Pixar. When you say, okay, I have this 3D space, I'm positioning sounds of objects in this 3D space. I have virtual cameras that move around and capture the perspective of everything. But now if you compare with the sound domain, exactly what we have is we have digital audio workstations like Pro Tools and many others that essentially it's the audio equivalent of a video editing software. So essentially you are mixing sounds on top of sounds. And yes, you may have some 3D features like a 3D panner or something like that, but actually it's almost like going to a Photoshop and say, let's have some perspective filter. And yes, it's 3D features, but it's not natively things in 3D. So what we decided to do with sound particles is to create a software that is based in 3D. So I'm not panning things around. I'm not mixing sounds on top of sounds. I have this 3D space, and now I start populating this 3D space with sound. And I say, okay, I have a sound here, another sound over there. This sound is moving in that direction. This sound is 3 miles over there. This sound is 300 yards over here. And I positioned the sound. And then instead of virtual cameras, I have virtual microphones. So I'm able to get a microphone there. It could be stereo, Ambisonics up to 6 orders. It could be channel-based audio. It could be Dolby Atmos bed, whatever I want. And now I move the microphone, and depending when the microphone is and how the microphone is moving, I'm capturing everything. If the sound is moving, I get the Doppler of the sound. So it's a different kind of approach. And off top of this, there is one particular feature that everyone likes, is that we use the concept of particle systems, so we can generate thousands of sounds around it. So the kind of application that is more common with sound particles is that, imagine that I want to create something like a battlefield. Instead of going to Pro Tools and say, okay, let's import an explosion here, another explosion there, another machine gun and a screen, and probably after 1 or 2 days, you have 60 tracks with 60 sounds playing at the same time. You can eventually go to sound particles, and within 15 minutes say, okay, I want 10,000 sound sources. I want to spread this over a square mile. I want to import 200 war-related sound effects from a sound library. I want to add some random movements to simulate almost like soldiers moving around. And then I want to create random audio effects like random pitch shifters or random equalizers, and then have a microphone moving in the middle of the scene and capturing all of this. And when you start thinking in 3D, natively in 3D, and quite almost like organizing things like having a animation kind of workflow, there is several advantages. For instance, one of them, the example of the battlefield. The simple fact that you distribute sounds over a square mile means that you're going to have very few sounds close to the microphone and thousands of sounds very far away, simply adding to the rumble. So essentially you get both epic and detailed kind of sound at the same time. So this is pretty much the concept of sound particles, is to, okay, instead of using digital audio orchestration kind of approach and simply mixing sounds on top of sound, let's try to think this as a 3D, not as a panner, a 3D panner where essentially you are simply position things around you and you have a fixed listener position. No, let's think in 3D and say, okay, if I want to simulate a battle, let's place things like that. If I want to simulate a moving city, let's place some sounds like in a real situation. And by doing this, the kind of results that you get are even more interesting. And even sometimes even, of course, sound particles is a passion of me, so I could spend hours talking about, but even in terms of mixing, what type is, imagine that I have 2 sounds, okay, placed on Pro Tools, okay, and by having these 2 sounds, what is going to happen is that they are going to, some frequencies are going to collide, and they are going to collide on the exact same positions. If I place these 2 sounds in sound particles and they are slightly moving, okay, or the microphone is slightly movement, even movement like 1 meter per second or something like that, very slow movement, what is going to happen is that at some point, some frequencies are colliding between these 2 sounds, but as they move or the microphone move, now the frequencies start to collide at different frequencies, and this feels much more natural. And sometimes you get this kind of sound that is much more natural, and it's almost, you are almost astonished why this feels so natural, but essentially the simple fact that you are moving these frequencies that, of course, in the digital audio orchestration, they all will collide always at the same time, because we are simply mixing sounds instead of having this 3D approach to things. Just notice that I use also a question here from Jamie Scott regarding the plans for ADM export out of sound particles. Yes, we are working on that. We want to be able to export ADM for people to bring that into, for instance, Dolby Atmos or something like that. So that is something that is on the road.
We have 2 more questions left. One, let's see, Adela asks, in 7.1, 5.1, etc., is the audio that is sent to the LFE channel filtered in any way, or is it full spectrum mono copy of the full mix, and the limitations of the subwoofer itself does the filtering, cutting off the high frequencies?
So essentially, it depends on the formats. So there are formats that are directly, so which means that this what is sent for the LFE, it's directly sent to subwoofers, and all the audio that is sent for the main channels are going for the speakers. That are systems where you use bass management, which means that you can remove some low frequencies from the main channels mixed with the LFE and then send that to the to the subwoofer. So it depends on the format. With cinema, currently this doesn't use bass management with 5.1 and 5.1 to my information. So essentially what you place in the LFE channel goes directly for the subwoofer. If you talk about Dolby Atmos, I believe that Dolby internally is doing some sort of bass management to make sure that you get to the right LFE, because with Dolby Atmos you can get, for instance, 4 LFEs, each one at different positions of the room. So you can actually do this, some kind of bass management by Dolby, but is pretty much transparent to the users, which means that whatever you do on the studio, since you also pass by the same system, you are able to listen to what is happening. But with cinema, I believe that currently in cinema, you go straight for the subwoofer, what is on the LFE. But if you are using like home, like DVDs or things like that, most likely it's going to use a bass management system to do that.
Great. I'm trying to, I think, well, I'm going to try and squeeze in 2 more audience questions here. And Nuno, I think you can stop your screen sharing as well at this point. So we have a question from Alejandro. Do you provide any practical tutorials for recording, editing, mixing, and normalizing for 3D audio?
That is one of the things that we want to increase the number of tutorials that we have. Actually, COVID made us some impact, because we were preparing to start doing 1 or 2 videos per week, and now everyone went home, and at home we don't have the best acoustic, and we know that the people that our users are very keen about sound quality, and we cannot do a movie with some background noises, because otherwise the users say, oh, that's too amateur and so on. So that's, we want to definitely bring continue having much more tutorials about recording, mixing, and do all of those things for 3D audio. So to, once again, to continue our efforts to also help the community to get more information about all of this.
Wonderful. And final question of the evening from Bradley: is there an option to purchase a perpetual license for sound particles?
Yeah, you can either buy a perpetual license, or you can do a subscription if you imagine that you want to just try for some months and work that on a project or something like that. So it's up to you if you prefer a perpetual license, or if you want just a subscription for a few months.
Perfect. Nuno, thank you so much for your time. This was incredibly informative. I hope you all enjoyed it. And Nuno, I also just want to say thank you so much for staying up late your time to do this.
Yeah, once again, it was a pleasure, and don't hesitate to, you have my email. If you need anything, just let me know, me or anyone from the team at Sound Particles. So once again, I really hope you have enjoyed, and if you need anything, just let me know.
Absolutely. Thank you so much for your time, and thank you everyone for coming.
So, bye-bye, everyone.